For our fluid mechanical dissection, we were given an espresso machine. The members of our group include Frank, Alan, Abdul, Harrison, and Will. During the dissection, we found that the espresso machine possessed many unique features, and once we broke the machine down, we found that there are three main components: the water tank, vibration pump, and heating coil that make up the function to deliver coffee.
These are some CAD models we made. The top two were made by ourselves. The bottom one was found online. The bottom one is an exploded view of the vibrating pump. One of the elements we'll be analyzing later.
Here, we can see the machine overview, where the schematic on the left represents the key dimensions of the espresso machine relevant to our Bernoulli analysis. The vibration pump will be studied to analyze the increase of pressure on the fluid, and the heating coil uses conductive heat transfer to increase the temperature of the fluid, which also affects pressure, but this will be ignored for our analysis. Here, we can see the governing equations that we use to form our analysis. We use the definition of pressure for the vibrating pump, the viscous loss factor, and Bernoulli equations for quantifying the flow through the machine.
We had to make a few assumptions to simplify the mathematical analysis of our system. These assumptions are as follows: incompressible flow, steady flow, streamlined flow, uniform quasi-1D flow, no leaks in the pump, and a full tank of water.
So this is our vibration pump analysis. There are four distinct stages in a vibration pump water system. So first, stage one, the piston is in its retracted position and the valve is closed, with the water in position to be pumped. Through a no leak assumption and the quasi-1D flow assumption, we can use the hydraulic equation to get an estimate of the pressure generated by the pump. Stage two sees the piston fully extended, the valve opened, and the water flowing. With the assumption that the pressure in the chamber is constant, and with quasi-1D flow, we can estimate the rate at which water exits the valve through the use of Bernoulli's equation and a conservation of mass. State three is simply when the chamber is emptied of water and the piston is still extended and the valve is still closed. State 4 sees the piston arm retract and the water flowing back into the chamber. Abstractly, this is due to a pressure difference between the water in the reservoir and the air in the chamber. As the water flows back in, this pressure gradient approaches zero, thus restarting the cycle.
Assuming that the pressure added to the fluid is almost all coming from the stiff return spring pushing the piston, we can do a relatively simple calculation to find the increase in pressure on a chunk of fluid. We found the spring constant by using known weights and measuring the displacement, and by analysis of a video online, we found the displacement of the spring before the valve opens. Then, by measuring the area of the pressure chamber, the pressure was found, which came out to be around 2.5 megapascals.
For our Reynolds number analysis, we found the governing parameter values online. To find the velocity, we looked up the flow rate of the exact model of our espresso machine, and then divided it by the cross-sectional area of the pipe, and then we found our Reynolds number, which was 4945. Similarly, for viscous dissipation factor calculation, we found the surface roughness value online for nylon tubes because the pipe was made from nylon. Then we calculated the relative surface roughness and used that and the Reynolds number and the Moody chart to find the viscous dissipation factor of 0.4.
To find the fluid speed through the first tube, we applied conservation of mass between tube 1 and tube 2. And in this system, density is constant because of the incompressible flow assumption. And since we calculated the properties at state 2, we can find the speed at state 1 coming out to be 0.389 meters per second. From there, we have all the information to calculate the Reynolds number and viscous dissipation factor, resulting in 2482 and 0.5 respectively.
Pictured here are the streamlines. Using earlier calculations, we can find the properties of the flow at 5 site locations by using the Bernoulli constant and studying the losses due to pipes in between each location, as well as the increase of pressure that we studied earlier from the pump. We found that the expelled pressure was around 2.45 megapascals, which is right around the pressure a normal coffee maker expels fluid at, validating our analysis.
So we found the first tube to have laminar flow and the second tube to have turbulent flow, and this makes sense because the flow leading into the pump is more controlled due to the low velocity, and the flow leaving the pump is more uncontrolled because it is shot out of the pump at a higher velocity. And the Reynolds number is lower in tube 1 because of the lower fluid speed, and the viscous dissipation factor is also lower because of the smaller diameter, since viscous losses in a tube are dominated by the diameter. Overall, we had low Reynolds number value because of the small tube diameters and low fluid speeds, and this is expected for a coffee machine because you want to have a slow speed to ensure fluid interacts with the coffee particles, and you don't want anything to leak in the system.
With regards to practical implications, our mathematical model for fluid speed and Reynolds number line up with the expected performance of an espresso machine. If flow conditions were to change, say with the addition of a much more viscous fluid, we would see a cease in function. The fluid conditions we calculated allow for easy flow, no leaks, and plenty of time for the coffee to absorb into the water.